Thank you very much, everyone, for attending this presentation, and very pleased to be speaking to you. I would like to start off by thanking the organizing committee for this great conference, and definitely by thanking Dr. Ammar for this excellent presentation. I think he made my job here a lot easier by really setting things in perspective as to why we need to talk about the Aqaba Bay incident in general, and why does it matter for everyone who works in process safety. This incident that took place is quite a special incident for Jordanians and fresh in the minds of Jordanians, but it's not necessarily very well covered internationally or hasn't gotten enough echo. And this is why we are very keen on taking a closer look at this incident and trying to extract as many lessons learned so that everyone can make use of those lessons and actually prevent such incidents anywhere around the globe. And with this said, I'd like to just first start off by telling you that this is not an incident investigation per se. This paper was written based on whatever information we were able to arrive at, and it's just a professional interpretation of what has taken place here in Jordan and how we may work all together to prevent such things. I'll start off by introducing myself to you, your speaker, Hamid Al-Nahawi. I'm a chemical engineer by profession, did my bachelor's in chemical engineering and currently doing a master's degree in engineering management. I've been working in the process safety consulting sector for about 4.5 years now, and I specialize in pressure relief and flare systems design. So this is just a brief introduction as to who your speaker is and my relationship to the topic that we will be talking about. To start off, I'd like to give you a brief outline on what this presentation is about. We're going to start off by introducing some background regarding what the Port of Aqaba means to Jordan, what this location means in general to the incident and its importance. And then I'll briefly touch upon chlorine toxicology and information regarding chlorine, just to set things in perspective for everyone. And then we'll have a closer look at the incident itself, the consequences that took place and the risks that are associated, and the lessons that we were able to extract as a personal or professional interpretation, I should say, of the incident. I'd also like to draw your attention to the fact that this paper in this presentation was also highlighted in the CCPS Safety Beacon sponsored by our company, IOMosaic, and it was also presented in the Global Process Safety Congress, so that this incident in general takes enough international echo. So to start off by setting things in perspective and where this incident took place, it took place in the Port of Aqaba, and as the Jordanians would know, maybe not so much the international guests here, that the Port of Aqaba is actually the only access that Jordan has to the sea. And this makes it a very, very critical place, not only for tourism, but also for cargo, and it also has about 20 million tons per year of cargo traffic going through this location. It's also a restricted geographical location, which makes such an incident in such a very confined location geographically more and more dangerous. And thankfully, some of those factors were mitigated by the conditions that were prevalent during the time of the incident, as we will see later on. So what happened, what took place was that on the 27th of June last year, there was a transportation intended of some chlorine tankers that were being lifted onto a ship, and those ISO tankers containing about 25 tons of liquefied chlorine were being lifted, and at that time the lifting cable snapped and dropped the chlorine ISO tanker onto the ship, causing it to catastrophically rupture and causing all the chlorine that was within the ISO tanker to immediately vaporize and spread into a vapor cloud, causing the subsequent death of 13 individuals and more than 250 injuries at the time. Chlorine in general is dangerous, and Dr. Ammar touched upon this. We understand that chlorine is dangerous, but we understand that it is also very important. It is very important because we have a lot of uses for it, and some of those critical uses cannot, at the time being, cannot be substituted immediately by something that is safer. Chlorine is used as a disinfectant in some water treatment processes, whether for drinking water or wastewater treatment. It's also used in food processing and used in paper mills and used in production of ethylene dichloride and production of PVC in general. You may even be interested in knowing that over half of all of the industrial chemical processes include the use of chlorine, and it's actually used up to a 90% level in pharmaceuticals and perhaps slightly even higher in crop protection chemicals. With this said, chlorine needs to be transported safely because we understand it is quite dangerous to carry. And we carry chlorine in ISO tankers. This is a common method to transport chlorine in ISO tankers, which are specifically designed to carry dangerous goods, whether in the liquid form or potentially in the vapor form. And you can think of those ISO tankers, you can think of them as small portable pressure vessels. They are designed to withstand design pressures up to 250 psig and can also work at pressures around 220 or slightly less psig. So this is quite a high working pressure, and they can carry also large volumes ranging between 21,000 to 40,000 liters. They are, as I said, quite reliable, quite cost effective, and it has been a very common way to transport certain chemicals, especially because we learned how to deal with ISO tankers and we learned how to carry them well, and we find that the level of risk associated with transporting certain chemicals using ISO tankers is generally acceptable level of risk. So chlorine as a chemical itself is a yellow-green vapor at room temperature, and it has quite a pungent and irritating smell. It is also approximately 2.5 times heavier than air. So as we will see when we're looking closer at the incident, chlorine tends to settle around and not to spread very easily. It is not flammable, however, if it was, then we would have been looking at risks of explosions or risks of vapor cloud fires that could have taken place at the time of the incident. Chlorine is also slightly soluble in water, and once that takes place, there are some reactions that can take place as well with chlorine, which allows it to generate hydrochloric acid or hypochlorous acid. Those two chemicals are actually what make it quite toxic to the human being, because once it enters the lungs, it starts to form those acids and to damage the lungs, and essentially the person ends up drowning because the lungs start to fill up with liquid, which is not the intended way for the lungs to function. Chlorine toxicology can be looked at in more detail when it comes to process safety and risk management, and there are officially published limits for different toxic chemicals. The acute exposure guideline levels, or AEGL, those are limits that are published by official bodies that tell us both that quantify the risk in terms of levels, and we look at factors including exposure to concentrations of chlorine and the duration at which you are exposed to chlorine. So we can see that there are categories. Level 1 is where you experience notable discomfort and irritation, however, not necessarily any symptoms that would last or anything that would be dangerous to health on the long term. On level 2, there are some irreversible and other very serious, long-lasting effects that the person will start to experience because either they have been exposed to this toxicant for quite a long time, or they have been exposed to the toxicant at relatively high concentrations. And at level 3, we will start to experience fatalities, unfortunately, and health effects that are quite severe to the human being. So we can immediately infer that the 13 casualties that happened were exposed to chlorine concentrations at level 3. Looking closely at the incident now, and to start looking at the details and then extracting the lessons from this. The time of the incident was luckily caught on CCTV, and this allows us as process safety professionals to chase after the details and try to learn from them and to reconstruct the incident that took place, because modeling incidents is a very good way to understand that should certain conditions have been different, maybe the consequences would have been even a lot worse than what we have seen. And this is what we will come to touch upon in a few minutes. So at the time of the incident, this screenshot is taken 1 second after the impact, 1 second after the catastrophic failure of the ISO tanker. And we can see that there is a very distinct yellow cloud that is forming around the ship. And if we look closely at the color, this color, it is not a transparent cloud yet, and it is bright yellow, telling you that the concentration is still high at that place. Looking just 3 seconds after that screenshot, you can see that this cloud is starting to spread over. However, it has not mixed with air or spread outwards. It started to actually fall downwards towards the ground and to spread along the ground. So at this point, we definitely know that there are some employees and some staff that were around this cloud that were being directly either engulfed by this cloud or being exposed to the concentrations therein. And slightly after, at 6 seconds after the impact, you can see that the color of the cloud now started to slightly dilute. The cloud is more transparent and is trying to move and trying to spread and disperse. However, it is still quite visibly yellow, and we can tell that there are still quite high concentrations at this point. So what we ended up doing when we were trying to look at this incident is that we used our proprietary and industry-grade software to try and model the incident that took place. So we used our software called SuperChems to try and model this and see how the cloud dispersed according to the givens that we had. So we tried to recreate this to understand and to sort of chronologically model the situation to see how the consequences looked. And as you can see on the left-hand side, this is a screenshot of the vapor cloud that formed and how over time it spread in the geographical location of the incident. The meteorological conditions that we used were taken from the published meteorological conditions at the time of the incident by the US Department of Commerce, National Oceanic and Atmospheric Association. So we used temperature at the time was 33 degrees, the pressure was about 106 HPA, and the wind speed was 5 meters per second. And the wind direction was northerly to an extent at 347 degrees. Then we had to infer an atmospheric stability class and a toxic criteria. So based on the conditions, it seemed logical to infer an atmospheric stability class of C. So to model the situation, we also tried to look at the conditions within the ISO tanker right prior to the catastrophic failure of the tanker. So we mentioned that ISO tankers generally operate at around 220 or 217 psig, and that was the starting pressure that we chose, and starting release temperature of 91 degrees Fahrenheit, and a total inventory of 50,000 pounds within the ISO tanker. We also visually and scaled the images that were provided to us, and we were able to estimate the hole size and the area of the holes that took place. So we can see that there are two notably large holes or punctures in the ISO tanker, and we have combined those into a single area for simplicity and used a very conservative discharge coefficient. So as you can see, this is a curve for the depressurization of the tank that took place, and we can see that really the contents of the tank were almost immediately depressurized, and very swiftly within about 0.04 seconds the entire inventory of this tank was released to atmosphere and thus vaporized as well, encompassing the area in a split second, as we say. So we can also see the venting history, and we can see that the entire mass as well was able to escape this tank in a very short period of time. Then we look here at the cloud that drifted and at the different AEGL levels that we were discussing. So we set the AEGL levels, and we tried to see at each level to which extent or to which downwind distance did the cloud spread. And you can see that at AEGL levels 1, the relatively safe but slightly irritating levels, the cloud has spread quite distantly to about more than 14,000 meters. However, the actual AEGL 3 level cloud was also engulfing an area of about 3,000 meters, around 3 kilos in radius. So the consequence model was, we were able to infer from this model that thankfully, and because the conditions were warm and slightly windy during summer, and because the prevalent wind direction was favorable, the cloud ended up moving in areas with less inhabitants. Should the conditions have been different, potentially this vapor cloud could have moved in areas where tourists were located on the beaches of Aqaba, and we would have been looking at a very more catastrophic situation. Not to say, of course, that the situation is not catastrophic as it is, because one fatality is too much and one accident is too much. But we can still learn from this and we can still improve. So thankfully, the prevalent wind directions were favorable. Also, the incident generated a huge media coverage, and there was immediate pursuance from the king himself, and immediate instructions to the government to take immediate actions to start investigating. And this is something we don't typically see internationally, that such an incident, investigations end up taking too long sometimes. And sometimes they take periods of up to 1 year or even more, by which time people would have forgotten some of the details. I'm talking about the general public, and the topic is not as relevant to them. But fortunately, in this incident, because of the immediate media coverage, because this became more or less a matter of public perception as well, investigations were quite prompt and actions were also quite prompt. The primary cause, as we said, was the use of improper lifting equipment. The equipment that were used to lift this tanker onto the ship were out of spec, were not properly designed. Actually, people did not really know what the design parameters of those equipment were, and hence, and they were also fatigued and overused, and hence the accident took place. The lifting slings were designed for a maximum load of about 8.6 tons, which is almost 3 times less than what it was actually carrying at the time. With this said, we'd like to also draw your attention to the fact that we are not even certain that those equipment were designed to 8.6 tons, because they didn't have any nameplates or any documentation that can actually support the perceived design of the equipment. The investigations revealed that there was only this was only the second time that hazardous chemicals were being handled at the specific port location, and with this, the port staff were not adequately trained or were not competent to be dealing with chemicals. There are some investigations, they also tell us that some of the staff members were not aware whether the tankers were full or empty in the first place. So they didn't know what they were carrying, and they didn't know how dangerous this was. And this could be inferred by seeing the CCTV images that show some individuals running towards the cloud, not away from the cloud at the time of the incident. Also, the failed cable was, as we said, worn out. It was rusted. It was lacking technical specifications, as officially phrased by the investigating committees. There was non-compliance in general in safety procedures at the port facilities, and there wasn't adequate supervision during the time of the incident. Supervisors in charge of the safety of certain hazardous procedures like this were not available at site during the time of lifting those tanks. So the investigations thus tell us that supervisory role was almost completely absent, and the general lack of safety culture at the location at the port facilities was identified as the major and root cause of the incident. So the direct cause would be the use of improper lifting equipment, but the root cause is the complete absence of safety culture in the ports. With this said, we can use this information not necessarily to for purposes of accountability, which is important when we have accidents, but we are only, in this venue, we are discussing this for recommendations, conclusions, and to be able to learn from such incidents and prevent their repetition. So one lesson learned is that we need to all understand the risks associated with any process. There isn't a risk-free process, and we cannot avoid those risks, but we can mitigate those risks and bring them to levels that are generally accepted so that incidents are not taking place or they're not fatal to people. We can ensure proper training for personnel who are being involved, and as the minister himself said today, it is the right of the employees to be working in safe environments. So we need to ensure as process safety professionals and as people in charge, that the staff are trained well and they are able to handle the equipment and able to handle the chemicals should anything go wrong. Hazardous materials should only be handled by competent bodies and well-trained staff, and this is very important to understand, because permitting anyone to do such operations will end up inevitably causing some sort of incident which can be as catastrophic as we saw. The use of certain procedures and processes is also a good recommendation. In lifting and port facilities, process safety management is not necessarily applicable in terms of if we look at the 14 OSHA elements or other process safety management standards. However, it's always good to use them because they're only going to help you improve your process and keep your process safe. So the use of things like management of change or the issuance of working permits, those things will definitely ensure that you have a generally more controlled process and a generally safer process. They will also ensure that risks are identified beforehand and that suitable procedures are employed beforehand. So safety culture in general in a working environment should be instilled at all levels, starting from the most basic staff members up to the management, and as far as it needs to be instilled so that people will generally adopt this safety culture and understand how to protect themselves and to protect others. Also, we need to identify that the port facilities, as I mentioned, are not necessarily covered by process safety management procedures. However, highly hazardous chemicals, it's always a good idea to use internationally recognized and internationally employed standards and procedures to control the use and the operation of processes that involve transportation of hazardous chemicals. Thank you very much for attending this presentation. As I said, this was an interpretation of what took place, not necessarily an incident investigation. And the work is definitely up for upgrade and update based on any further information that could be provided to us, more details, and we welcome all of your inputs for this presentation. Thank you very much.